In this presentation, we will be discussing the discovery of a gravitationally lensed quasar at a redshift of about 6.51. In 2019, a paper was published presenting the findings from astronomers of the Gemini Observatory. These astronomers stumbled upon light emitted from an extremely distant pulsar at a redshift of about 6.51. This light was emitted a few 100 million years after the birth of the universe. The high redshift of very distant quasars can be explained by the expansion of the universe. It results in more distant objects moving faster away from us than the closer objects. This outwards acceleration causes light waves emitted from the objects in space to be stretched slightly as the object moves away from us, lengthening the wave. This lengthened wave therefore appears redder, and thus the electromagnetic spectrum emitted is shifted towards the red side of the spectrum. This is called redshift. The quasar was only able to be seen due to an obstructing galaxy acting as a gravitational lens, bending and magnifying the light reaching the telescope. This remarkable observation opens up a world of possibilities to observe quasars and other very distant objects previously missed using standard color selection techniques. In order to understand this phenomenon, we need to fully grasp exactly what it is we are looking at. Quasars are very luminous and highly active galaxies located at very far distances, mainly at the edges of the observable universe. Only emissions from the highly active galactic center are actually observed, and sometimes it's then called an active galactic center or an AGN. The light that we detect today from quasars was produced in the infancy of the galaxy, as these objects are located at such a far distance from Earth. Some are actually seen only a few 100 million years after their birth in the Big Bang. The intense radiation we observe from quasars are thought to be powered by a supermassive black hole at the galactic center, where the accretion disk orbiting the center is heated to extremely high temperatures, generating radio waves, X-rays, ultraviolet, and visible light. Highly redshifted quasar detection is difficult due to their vast distance from Earth. However, gravitational lensing provides a way of observing quasars with high magnification due to the distorting and magnifying effects of a high-mass object in the same line of sight. The discovery of quasars came from their observed spectrum showing unrecognizable emission lines. Elements were present in the spectra which should not have been. Dr. Martin Schmidt suggested that the emission lines were very redshifted, and thus the quasar was very far away. This explains the spectra observed and correlates with the expected emission lines.
In order for the lensed quasar to be identified and imaged, it took the collaborative effort of selecting the right target from the UK IRT Hemisphere Survey, the Pan-STAR-1 survey, and the Wide Field Infrared survey. After which, it fell on the hands of the binospec optical and the low-resolution imaging spectrographs to make follow-up observations. It was from the former where evidence of a strong Lyman alpha emission was found. Penultimately, the Gemini North and Keck 1 telescopes sealed the deal, with their optical and near-infrared instruments confirming the earlier data. But the data still wasn't clear enough, so the Megalin 1 telescope and the Large Binocular Telescope were also needed, both using advanced adaptive optics to take near-infrared readings. Once all the data was combined, it became clear how truly extraordinary the target was. Despite the ever-so-elegant name of J0439 plus 1634. Just rolls off the tongue, doesn't it? It was through these numerous observations that the astronomers were able to identify the profile of the element key to narrowing down how far, and subsequently old, the target was: singly ionized magnesium. With the help of good old MG2, a definitive redshift was achieved. This was used to calculate the distance, given that distance is directly proportional to redshift via the Hubble constant. With bated breaths, the astronomers saw that they discovered the brightest quasar ever, at redshift greater than 5. Now, this was astonishing for two reasons. One, it meant that this was one of the furthest quasars we've yet to observe, giving us a glimpse into the conditions of the extremely early universe. And two, you're not supposed to find quasar emissions at this wavelength. At the very least, the IGM's optical death should make it incredibly improbable, if not impossible. They only managed to image it because the gods of astronomy looked down on them and aligned the stars, both metaphorically and literally.
Okay, so why do we see these effects? Why do we get these images? Well, this is due to gravitational lensing. This occurs when the gravitational field created by a large amount of matter distorts and magnifies the light from a distant source that is behind it directly in the line of sight, similar to a magnifying glass. When a concentration of matter, such as the core of a galaxy, causes the gravitational lensing of another object, the light from this object is redirected and magnified around it, often resulting in multiple different images of the background object. In the context of the quasar in this paper, it is gravitationally lensed by a foreground, very faint galaxy, which causes the light from the quasar to be magnified and redirected. A lens model fit to the data resulted in the likelihood that the gravitational lensing was producing 3 images of the quasar, such as in this picture, where the white crosses indicate the locations of the best fit quasar images, and where the red and blue lines represent different properties of the lens. The faintness of the foreground galaxy, combined with a high apparent luminosity of the quasar, results in the flux of the lensing galaxy having a minimal impact on the unresolved total quasar, plus lens color, which was used in the selection of this quasar as being a lensed high redshift candidate for study. If the foreground galaxy was only 0.5 magnitudes brighter, this quasar would not have fitted the color selection criteria.
If nothing else, this paper is a reminder of the adaptability that is required of astronomers in order to rethink the limitations which we place on our observations, and what information we might miss out on in doing so. It is the opinion of this group that this paper achieves its goals in identifying and modeling the oldest known quasar to date, which just so happens to be gravitationally lensed. With the high quality and well-detailed structures of the methods the pioneers gave us, we can have better chances of finding more of these ancient gems so that they may illuminate the ever so dark, distant past.